of Technology, and he's also the Assistant Director of the New Jersey Coastal Protection Technical Assistance Service, which, as I understand, is kind of a state-funded function that the university plays to provide technical information. And he also serves as a Sea Grant Coastal Processing Specialist in New Jersey. So once again, you have 3 Sea Grant Coastal Processing Specialists in the room, which is kind of unusual. We usually don't get along that well. So yeah, thanks for coming up.
Thank you, Ben. I am the youngest of the coastal processing specialists.
But not the best looking.
Not the best looking, though. That's Spencer. Jay invited me, even though I am from New Jersey, but he made me promise to only talk about New York. So that's what I'm going to try and do. I'm going to talk about the Hudson River Sustainable Shorelines Project, which is a project that myself, as well as a bunch of our students at Stevens, have been involved in, probably going back about 5 years now. I think it's an excellent, it was an eye-opening project for me. I got involved as a coastal engineer. You saw in the Venn diagram earlier today the nexus of the different regions, and coastal engineering being one that sometimes is left out when we start to talk about living shorelines. Generally, the ecologists and the plant people don't like us engineers, and vice versa. At least traditionally that was the case. And hopefully through this project, we're all working together. It's a good example of working together for some excellent results. I want to acknowledge Andrew Rello, one of my PhD students, who also helped me with this presentation and has worked on this, as well as a cast of thousands. I just listed a few there. No relation between me and Chris Miller or Dan Miller, but we'll open the 3 Millers consulting after this. A lot of people worked on this from a lot of different agencies. New York State DEC, as well as the Hudson River NEARS program are the kind of the main folks, but also the ecologists from Carey Institute and us at Stevens. And we all bring something different, which I think makes it interesting. All right, don't read all the, just worry about the bold stuff. This is kind of the definition of the Sustainable Shorelines Project, taken from the Sustainable Shorelines website. The goal is to provide science-based information about the engineering, economic, and ecological trade-offs involved with shoreline stabilization options, particularly in the Hudson River estuary. Primarily, this project is focused from the Tappan Zee Bridge up to the dam at Troy. So it's the upper part of the Hudson for the most part. Here are again, the overarching objectives of the project. Characterize the present and future conditions of the estuary, considering things like sea level rise, of course. Determine these ecological, engineering, and economic trade-offs of different shoreline management options, understanding that in each situation is different, and which of these factors weighs the most depends oftentimes on where you are and what the purpose of that shoreline is. Characterize where the decisions are being made with regards to shoreline stabilization. In other words, identify the key points at which you can influence that decision, so that we can start to consider more of these sustainable shorelines projects. Demonstrate innovative shorelines and best management practices. So demonstration sites are great. Demonstration sites also cost a lot of money. So we've actually started to kind of capitalize on sites that were constructed not necessarily as living shorelines or sustainable shorelines, but kind of projects of opportunity that we can look at and hope to learn from. And last, create some decision support tools, and then communicate the results through various outreach activities. Being here today is an example of just one way in which we're trying to do that. Okay, to save time, this is the Hudson River estuary, some tidal wetlands. Hudson River estuary, some people don't realize it, but it is an estuary. It's a very diverse estuary. The width of the river varies greatly from the Tappan Zee up to the dam at Troy. The depth varies significantly. You have embayments, you have deep, narrow channels. Basically, you have it all. So in one sense, the Hudson River estuary is sort of an ideal location to do or to look at because there's different opportunities depending on where you are within the estuary to attempt different sorts of non-traditional or sustainable shoreline stabilization options. Okay, so I'm just going to talk through or go through some of the tasks or some of the things that we've done so far to date and some of the information that we've learned through this process. Here you see the first 3. Pace University performed a review of legal instruments for shore zone protection. In other words, looking at all the regulations that govern what you do on a particular shoreline. Again, looking for opportunities to influence the process along the way. We had Jerry Stedinger from Cornell do a storm surge model looking at sea level rise scenarios. Very simple one-dimensional model, basically illustrating storm surges propagating all the way up to the dam at Troy. And then what you see in blue there, I'm going to start to go through a series of some of the tasks that I'm going to get to in a little bit more detail than just a cursory explanation of the first two. First thing that we realized is terminology was ill-defined. I think one of the earlier speakers had, Jake, in his introduction, talked about living shorelines, sustainable shorelines, green shorelines, all these different monikers that we use to describe kind of what we're doing. So to try and kind of bring it all together, at least for our project, as far as we were concerned, we had a terminology definition document, which was created by Emily Hauser from Herner. One thing that we did on purpose is we decided on sustainable shorelines. We got away from living shorelines because one of the things that we found in New Jersey is when we talk about living shorelines, there's a whole group of people that feel living shorelines are plantings and vegetation. And if you have rock, rock is not living, rock is not a part of a living shoreline. As you've seen this morning from a lot of the presentations and a lot of from Maryland and North Carolina, states with more experience, rock is often a component of living shorelines. So to kind of avoid this, we settled on this definition, what we call sustainable shorelines. And what we define sustainable shorelines is, you see that definition below. It says shoreline management practices that seek to protect the shore zone's wildlife habitat, ecological benefits, outdoor recreation, community quality of life, and water-dependent businesses for future generations. So it's kind of broad, but that's kind of what we settled on. And the idea with this, or the intent, was to consider things that would be adaptable and include some sort of ecological aspect, and incorporate or include both soft and hard structures. Again, recognizing we're working on the Hudson River. So there are areas of the Hudson River that are bulkheaded, that need to be bulkheaded. We're not going to get rid of every bulkhead. So by saying sustainable shorelines, can we take these bulkheaded shorelines and make them more attractive from an ecological standpoint? So kind of looking at a very broad spectrum of opportunities and options. Just another definition, we focus our work on what we call the shore zone. So in other words, it's not just the shoreline. It's not just where the water meets the land. It's the entire shore zone. So that incorporates some of the subaqueous habitat, as well as some of the upland areas. You see the definition on the bottom. I don't know if you can, it shows up actually better on the screen than on mine. But the shore zone we define as the region closely adjoining the shoreline in which strong and direct interactions tightly link the terrestrial ecosystem to the aquatic ecosystem and vice versa. So you saw a very similar definition on from one of the previous speakers. So that's kind of the area that we're focusing on. What happens in that shore zone, because that's, from an ecological standpoint, certainly a very important area. One of the first tasks that was done is we surveyed shorelines from Troy down to the Tappan Zee Bridge. This is performed by Dan Miller from Herner. Some of the results, or what he found, is that there was over 300 miles of shoreline in that region. He found that there were natural shorelines along 47%, riprap on 30%, bulkhead and cribbing on 11%, what we call remnant engineered structures on 12%. That's essentially engineered shorelines, bulkheads, cribbing, etc., that was in some sort of dilapidation or failing at this point. Interesting thing about those areas is there are opportunities. They're not just problems, they're opportunities, because there's an option, or there's a chance to go back and kind of think about what's going on there and see if we can try something a little bit different, or even capitalize on some of the infrastructure that's there. Some of these old bulkheads actually function sort of like the low sill that Spencer talked about earlier. So we have a variety of different existing shoreline types. We have a very strong team headed by the ecologists from Cary, looking at all the ecological aspects. Jay said I'm a coastal engineer, so I know very little about the plants. I've learned a lot today so far. Every time I listen to Chris, I learn more and more. It's amazing. But the folks at Cary, basically we're looking at the ecological function of different shoreline types. What's the ecology like in front of a bulkhead, in front of timber cribbing, on a riprap slope? What are the important aspects and factors to consider along all these different shoreline types? This is just a summary. I took it from one of their slides, or one of their presentations that they had done. Some of the findings that they found. Some of this is not necessarily unexpected, because the conditions vary so widely. The ecological characteristics and functions also vary widely across the Hudson River shore zones. Some variation is explained by the shore type. Again, engineered structures tend to have poor ecological function. than natural shorelines. Again, maybe not necessarily surprising, but certainly validated in this region. And some of the variations explained by physical characteristics of the shore zone, and we'll get into this in a second. Certainly, some of the things that we've traditionally known about shoreline structures and shorelines in general are kind of proven true here. Factors such as roughness along a shoreline is important. Sinuosity along a shoreline can be often important for ecological function. Slope is important for sure. So some of these findings were also borne out in some of their results. But then, perhaps dishearteningly, the last bullet says much of the variation is unexplained. So there's a lot that we know, there's a lot that we don't know, and we're continuing to kind of hone in on these factors that we don't know. This is just a kind of a screenshot of a brochure. They're actually out on the registration table. I brought a whole bunch of them. And this is sort of one of the outreach materials that was generated from the ecological work. It's quick and dirty, 10 steps to better shore zones. So general guiding principles that they found through their work that lead to a better functioning shore zone. Again, an area from underwater area all the way up to the upland area. So what makes that function most in the best manner from an ecological standpoint. Again, we had a hard time with convincing people to do demonstration sites because they're costly and people need to be willing for them to fail, often in cases. So what we try to do is capitalize on existing or built projects and take information that we've learned from those projects and potentially carry them forward to design new projects within this area. So Herner put together an analysis of case studies. Case studies look at a lot of different aspects, everything from some ecology and engineering specifics to some more kind of social science questions. Why did people decide to go with this non-traditional, ecologically enhanced approach? At what point did they make these decisions? Again, trying to figure out how we could reproduce this in some demonstration sites and eventually in some more targeted stabilization activities. And it was great because there's an incentive to have some of the companies that worked on these projects get their work highlighted, so kind of free publicity for them. So there's a series of five studies that have been completed so far. Each has a sort of a workup like this. This is all available on the Sustainable Shorelines website, which I'll put up as on the last slide that I'll present. But there's 5 of these case studies. They're each maybe less than 10 pages long. Nice, not too difficult to read. Goes through each of the sites. This is actually an interesting one, the Coxsackie boat launch. Talk about kind of looking around and seeing what's in the vicinity, trying to capitalize and recreate what's there naturally. If you can see, this was, the stabilization project here was, let's see if I can get this thing to work, right in this area here where there's no vegetation, or basically it had eroded back to the parking lot. And the difference between this area here where you see strong vegetation and the area where there's none, offshore the area with strong vegetation, there is a shipwreck called the Storm King, which essentially is functioning as a natural sill in that area. So the project here actually capitalized on that and said, well, let's try and recreate sort of a sill in this area where there's no protection using rock and a terrace kind of structure. But they constructed a project here, and so far it's been pretty successful, and it made it through a couple of storms. The current case studies that, again, there's 5 that have been, 6 I guess, that have been done so far, and there's other ones being added kind of as we find them, we're adding them to the site. Engineering analysis is what we've been looking at here, looking at Stevens. We've done a variety of different things. These range from the first task we were assigned is to look at, or to do a literature review of existing shoreline stabilization techniques for sheltered shorelines. So this is reviewing a lot of Scott's work, a lot of the work that's been done in Maryland and in North Carolina. And we settled in on 29 different techniques. It isn't much more than this. It's just you have to draw a line somewhere between the variations in some of these techniques. So we looked at traditional approaches for stabilizing shorelines, bulkheads, gabions, groins, revetments, to some hybrid approaches, sills, live crib walls, joint planting, biowalls, to just some more natural approaches, living breakwaters, oyster reefs, coconut fiber roots, things like that. So this literature review looks something like this. Very short 2-3 page summaries of each type of technique. We're very consistent with the way that we did it, so for each of the 29 techniques there's something that looks just like this. The headings are all the same. In particular, we have like a little key up at right underneath the technique. It describes the application, whether it's on a scale from soft to hard, construction costs generally from low to high, maintenance costs from low to high, and adaptability from low to high. And we kind of did this for each of these techniques. Then at the end, there's a summary, so you can at a quick glance kind of look and go back and forth. I should mention that all of this work has been vetted through our advisory committee that we have. It includes a bunch of engineers, landscape architects, policymakers. Some people in this room are on those committees. So we have a glossary at the end as well. We talked a little bit about cost. We also did a comparative cost analysis of different approaches. We were tasked with 3 different sites, 9 different approaches at each site, looking at 2 different sea level rise scenarios. So this was quite extensive. So the cost analyses we did were necessarily quite limited. Basically, we tried to estimate the important quantities that we would need to develop some sort of representative cost estimate. These cost estimates were not intended to be used by a design engineer if they were going to go to a site and wanted to build something. It was more to be consistent amongst the techniques and develop sort of a framework for comparing costs across different approaches. We considered a 70-year time frame, so it's sort of a life cycle cost analysis. The costs included different categories. There was the initial construction costs based on material and labor, maintenance and repair costs, damage costs, and then replacement costs for structures like bulkheads, which have a limited lifespan. You would assume over 70 years you'd have to replace the bulkhead once or twice. And at the end, we ended up with a finished product which looks something like this, comparing the different approaches at each of the 3 different sites. I should mention the 3 different sites range from Poughkeepsie, which is a very narrow, very steep shoreline, deep channel section of the Hudson, to Henry Hudson Park and Bowline Point Park, which are more bay shore type sites. So from high energy basically to low energy. And generally the conclusions that we reached were that several of the alternatives are relatively similar in terms of cost, including some of the ecologically enhanced or sustainable shorelines techniques. And a lot of this comes down to, particularly with the bulkheads, the fact that at some point they have a limited lifespan, you'll have to replace them. Some of the rock structures, again, rock, if it's done correctly, technically would have a sort of a perpetual lifespan. We've also looked at a lot at Stevens at some urban solutions. This is some of the work that we've done prior to the Sustainable Shorelines Project, looking at what can be done along coastlines, for example, off of Manhattan and the waters south of the Tappan Zee Bridge. And the thing is that, again, the point here is that there are opportunities to enhance the ecological aspects of a project, even in these very urban areas. Project we were particularly involved in at Stevens. This was before I got to Stevens, but it was a Design in the Edge project along the Harlem River. Basically a dilapidated, kind of rundown shoreline, failing bulkhead and riprap, and the idea was to improve the site, but also include some access to the water. So it was it wasn't just a shoreline stabilization, it was a sort of urban park revitalization project. Very successful project. You see some before shots here. Even included some physical model testing that we did in Davidson Lab. Basically, we were looking to test different types of shorelines and see how the currents behaved in these little pockets. So the sinuous kind of terraced structure you see, the idea is to create a pocket of calm water being an area where fish can come and rest and hang out, and the big fish can come eat the little fish, and such as life. So we tested a variety of different scenarios there. This is an example of what the finished product looks like. It's actually a combination of all sorts of techniques. So you've got elevation changes, you've incorporated some slope here, you've incorporated some sinuosity in the shoreline, even though the actual shoreline is basically straight. These tide pools create sort of an artificial or a sinuous shoreline. Different types of materials, so there's obviously some vegetation here, there's rock involved, there's actually gabions at the base of the structure, so wire mesh cages basically filled with oyster shells at different areas. So it's a really great project which kind of illustrates a lot of the different things that you can do, certainly still in an urban environment and keeping sort of a hard edge, but softening it somewhat. This is another project I became intrigued with. This is a project in the Cuyahoga River, one of the most polluted water bodies in the U.S. Again, very urban shoreline, steel bulkhead, failing bulkhead. What can we do to kind of soften that? A variety of different options. options were come up with to stabilize this shoreline. Everything from these option one, which are these we call chubs or hanging baskets, essentially planter baskets hung over the edges of the bulkhead, just to put some vegetation back into the water. To these kind of pocket habitats and tiered walls, and these kind of resemble some of the Designing the Edge, what was ultimately constructed in the Designing the Edge project. Ideas, areas for boats to come up to the bulkhead. So finished product, this is an example of one of those hanging baskets. Again, it's basically essentially just a planter basket. Okay, and why even show this? I mean, this is kind of an ugly picture, I think, still, but it's more the illustration of, even for very low cost, some of the small things that can be done to certainly improve some of the ecological function of the areas, of these urban areas. We've also looked a little bit into alternative concrete solutions. Concrete has a problem with the pH. Marine organisms don't necessarily like to attach to it. This is actually my PhD student Andrew Rella's work. He's done a lot of work with this. So it's bad for biological recruitment. So can we alter sort of the concrete mix? We alter concrete mixes for a variety of other reasons. Can we alter it to enhance the habitat value? And the answer is yes. And he's worked with a company called CRC, which is very active here in the U.S. Basically altering the pH value of concrete so that, and as well as texturing the concrete, that's something else. Organisms don't like sheer surfaces, so if you can texture the concrete, you can change the pH value, you can get things to stick to it and grow on it, which, for example, oysters is something that they're very into, and oysters have the benefit of cleaning the water as they filter feed, so you can do things just with the materials that you use. Mentioned that Andrew's dissertation research actually got selected. Some of you may have been to the Changing the Course competition the New York EDC sponsored. His project actually won second prize there. And his project is basically looking at methods to increase the ability of oysters to encapsulate piles. So the idea of creating oyster cages around piles, but using a sort of a unique downwelling pump to circulate water to get oysters to grow in areas of the water column where they typically wouldn't be able to. So it's an innovative wave-powered pump. That was his dissertation research, and he took the application is an application specifically for the project. So it's a pretty neat and interesting project. So I invite you to ask him if you're interested later. Last thing that we did is we did physical forces characterization of the Hudson River environment. The idea being that we saw a lot about fetches and waves and whether or not these projects can grow. In the Hudson, we wanted to characterize the environment, recognizing that there are big areas, large areas of the Hudson River where some of these projects may not be appropriate. But if we understand better the physical forces ranging from wakes, ice is a huge issue up here, water levels, currents, bottom shear stresses, those types of factors. Those are things that we typically use as engineers to help us design projects. It's also information that's never really available. The use of fetches, we use fetches because wind data and distances are easy to measure. So can we do a little bit better? So we did a project where we looked at characterizing the physical forces. We did a very cursory wake analysis. Basically, we set up and we did a visual wake measurement observation using volunteer students. So this was very low cost. Graduated rods that we made ourselves. We think we had spent $100 in materials at Home Depot. But we manned 32 sites over the course of 4 days. And we collected 1 day's worth of data at each site. Now that's not necessarily representative, but it's a start. It was just kind of like an idea of what we could do if we get some more money to kind of study this in more detail. We're developing an analytical model of wakes to kind of supplement this, but the idea is to get some characterization of the wakes and the boat traffic at each of these sites along the Hudson. We've collected ice information from the Coast Guard reports. Coast Guard goes out and records ice thickness, ice type, ice coverage, ice extent during the ice season. So we took all that information, ingested it, did some statistical analyses, and created an ice information layer. It's a GIS layer that's available on the New York State GIS Clearinghouse and also through the DEC's, what's it called, do you remember anything? The data something or other. But it's all available in GIS, and the intent is to take the wake data and create something similar for the wake data. We used our high-resolution version of our hydrodynamic model that we operate at Stevens. It's called NIHOPS. It's a three-dimensional circulation model. We run it operationally. We do forecasts. We use it for things like forecasting storm surge during Hurricane Sandy. But for this specific project, we refined the grid. We brought it down to boxes, which are basically 65 meters square, so very fine resolution given the type of information that it spits out. And we used that to basically, we took a year's worth of data, we ran the model's been evaluated using all sorts of real data. We ran the model and we came up with a climatology based on 1 year's worth of data of the different variables that are important. Currents, waves, stresses, shear stresses, vertical stresses. So some that are important for shoreline stabilization approaches and others that have more ecological implications. And this is what our model grid looks like. The colors here on the Hudson are basically the color coding. I don't know if this is water level or currents, but it's basically, you get a color scale from high values to low values, so high currents to low currents. Again, all of this information is being translated into a GIS kind of environment. We're doing a statistical analysis on the year's worth of hindcasts. The blue line that's very busy that you see there, that's a time series of, I think, water level. And so we take that and we do a statistical analysis on it. We figure out what the median level is, what the 95% level is, et cetera. Get all these statistics. It's all available, again, plotted in GIS on a color-coded basis for mapping standpoint, but you can also point and click on each grid cell and get all this information. So you want to know what for that 1 year, what the median wave height was in that grid cell, you click on the box and it'll give you the median wave height, as well as all the statistical parameters. So it's a really useful source of information. Outreach and tool development, we're continually doing this. Being here is a part of that, just trying to let people know what we're doing. New York's a big state. We're working particularly in the upper Hudson. We got the lower Hudson. Here we're out on Long Island, Great Lakes. So we want to make sure that all this information gets transferred, certainly, to all the people that might want to use it. We've also done outreach to different groups, from engineers, landscape architects, to government regulators, trying to figure out what type of information they need and how to make it most usable. And we're continuing to refine the project. We actually just got a third phase of our project funded, found out yesterday, so we're kind of marching on with the Sustainable Shorelines project. This is kind of our group of partners and advisors. It's nice we get to meet up at Norrie Point a couple times a year. It's nice when it's a beautiful day like this. But you see, these are, again, our advisors come from all walks of life. They're regulators, landscape architects, engineers, developers. Bring everybody in and have them get a chance to comment on what we're doing and kind of guide the research as we go forward, which makes it kind of unique.